Hey everybody, this is Austin Hoggett here to give you another lecture from our OpenStax Intermediate Algebra textbook. Today we're going to start on Chapter 2, Solving Linear Equations. And our first section here, 2.1, is going to be on a general strategy to solving these types of equations. We have just a few learning objectives we're going to go over here. We'll talk about solving these linear equations using this general strategy, talk about the different types of equations that you can expect to see. And then we'll wrap up with some more complicated examples that include things like fractions and decimals as our coefficients for some of these problems. So let's get started on our first topic here, solving linear equations using a general strategy. So what does it mean to solve a linear equation? I'll skip ahead to a definition real quick. A linear equation looks something like this, where we have some coefficient times our variable of interest, usually just 1 for a linear equation, and we can say that we've got a solution to an equation if when we make a substitution for that particular value into the equation for our variable that we simplify and get a true statement. So what is a true statement? Well, something like 1 is equal to 1 we would say is a true statement. So you can imagine if I had something very simple, arbitrarily, let's say my example is something like x is equal to 1. Well, this is technically already solved as a linear equation. I can say with some certainty that 1 is the only thing that would make this statement true. And so sure enough, we would say that the variable by itself on one side of the equation equaling to some constant term is what yields a solution. But in general, we can say that if I just want to check if some value is a true solution to an equation, I make the substitution, simplify the expressions on both sides of the equation, and then just determine whether or not a true or false statement falls out of that. Okay, so let's look at an example of what I mean. Here we have a linear equation. Again, it's a little bit more complex in its format, but still maintains that ax plus b equals 0 sort of mainframe for building out more complex examples. So 5y plus 3 is equal to 10y minus 4 is our equation. We're asked to determine if y is equal to 3/5 or y is equal to 7/5 is a solution. So let's look at our first substitution here, 3/5. I'll just rewrite the statement here, substituting in that equation, and then simplify each side. So there's my substitution. When I multiply, let's say on the left-hand side of the equation, my whole number times this fraction, I can actually perform that calculation in two different ways. I can, for instance, multiply 5 times 3 to get 15 and then divide that value by 5. Or I could say 5 divided by 5 is 1 times 3 gives me 3. Ultimately, this fraction here will reduce to give me just 3, and 3 plus 3 would give me 6. On the right-hand side, I can simplify in a similar manner. I could, for instance, multiply 10 times 3 and get 30. Dividing by 5 gives me 6. Or I could say 10 divided by 5 is 2. Multiplying by 3 gives me 6. And 6 minus 4 results in 2. So I end up, after I've simplified both sides of the equation, with this statement that says 6 is equal to 2. Well, that we would say is a false statement. 6 is not equal to 2. And therefore, we can say that y equals 3/5 is not a solution to the original equation. What about our other value here, 7/5? Well, we can repeat the process and make that determination. So here I'll substitute in y for, 7/5 for y, and I get something like this. Simplifying in the same manner, again, I get fraction times my whole number value. The denominator and whole number 5 will cancel each other out. I'm left with 7 plus 3. That simplifies to give me 10. On the right-hand side, I get 10 divided by 5 is 2, multiplied by 7 gives me 14. Minus 4, I actually end up with the true statement now. 10 is equal to 10. And therefore, we can say that y is equal to 7/5 is, in fact, a solution to this equation. So I'll leave the top example here for you to try on your own. Let's do one more. Let's look at the bottom example now. So we have 9x plus 2 is equal to 6x plus 3. And again, we want to substitute in this fraction 1/3, x equals 1/3, to determine whether or not we have a solution. So again, I make my substitution, and notice that I'm maintaining the parentheticals here. That's a good general practice. And when I simplify, I will then have to consider if I get a true or false statement. So 9 times 1/3 will give me 3. 3 times 1 is just 3. So 3 plus 2 is going to give me 5 when I simplify on the left-hand side. 6 times 1/3, I end up with 6 divided by 3 is 2. Multiplied by 1 is still just 2. And plus 3 gives me 5. So yet again, I see I end up with a true statement after simplification. And therefore, we can be sure that x equals 1/3 is a solution to this example problem. So how do we solve equations using a general strategy? I glossed over this slide a moment ago, but let's go back to it now. If I want to determine the solution to any general equation, I need to be able to manipulate terms across each side of the equation using the two properties that I'm noting here. So we use the addition property of equality and multiplication property of equality to actually perform this generalized solution finding for some linear equation. So let's talk about these first before we show an example. The addition property of equality is fairly straightforward. We start with a simple statement like A is equal to B. Now, the addition property of equality states that I can introduce an operation of addition to both sides of this equation, and by adding the same constant term to both sides, I've maintained the equality, but I can actually change what the expression looks like by introducing that operation. And that's the premise behind using this general strategy. So what does it look like? Well, something like A equals B. Again, I can introduce a constant term to both sides. So by addition, and alternatively, this means maintains its equality if I were to use something like A minus C as well. And generally, we just say that this is the format that we use because the constant term could be both positive or negative and sort of encapsulates both of these conditions, right? Similarly, for multiplication property of equality, I start off with some initial expression A is equal to B, and this time I want to say that I can multiply both sides of the equation times some constant term. And again, we can say that division and multiplication would be similar in their operations and that it would also maintain the equality. So these four operations can be introduced to both sides of the equal sign that allows us to simplify a side but still maintain the equality of the original statement. So let's actually see how this is put into practice with our first example. So let's look at part 1 here, the very first question. I have something like 1/4 times x, 1/4 times x plus 2 is equal to 6. All right. Now, in this pattern, we can see that we have something akin to our original statement. Ax plus b is equal to some constant term. The original example said ax plus b is equal to 0, but again, there's some variations to what this can look like. So I have a coefficient on my x term plus some constant is equal to another constant. So the idea here is to actually isolate the variable of interest x. And to do that, I want to use those four operations that I mentioned a second ago, that addition property of equality and multiplication property of equality. So in this first example, 1/4 times x plus 2 is the expression I want to simplify. And normally when we think about simplifying the expression, we're considering what is the operation I can introduce to this side of the equation that actually reduce the number of terms down to where I just have the x term, right? So 1/4 x, we don't worry about the coefficient just yet, but I can introduce actually subtraction by 2 on both sides of the equation to maintain the original equality, but in introducing that subtraction by 2, actually reduced or simplify the left-hand side to be one less term. So 1/4 times x plus 2 minus 2. And of course, we subtract 2 from the other side as well. And often you'll see it written sort of just underneath the algebra. I'll do it in line here to sort of demonstrate what is actually being performed. So when we simplify here, I get something like plus 2 minus 2 is 0, and 0 plus 1/4 x is just 1/4 times x. And so I've actually been able to introduce an operation to maintain the equality while simultaneously simplifying one side of the equation so that I can finally isolate the value of x and then ultimately get the coefficient on that variable of interest to be 1. Now on the right hand side, I've got to simplify as well. I've got 6 minus 2 is equal to 4. And so at this stage, I've got variable term on the left with its coefficient and constant term on the right. At this point, we would like to introduce another operation, except this time we don't need to add or subtract terms from one side to the other. Actually need to multiply or divide. So in this case, I have a coefficient that happens to be a fraction. The easiest way to get rid of this fraction is to introduce multiplication by the reciprocal. So what is the reciprocal of a fraction? Well, we just interchange the numerator and denominator. In this case, my reciprocal of 1/4 would be positive 4. So here I'm introducing the operation of multiplication by 4 on both sides of the equation. 4 times 1/4, by its very definition, since it's the reciprocal, should give me 1. And 1 times x is ultimately, again, what I want to get. A coefficient of 1 on the variable of interest, and it's isolated by itself. And on the right-hand side, I get a constant term, x equals now 16 is the solution I come up with, right? So there you have it. There's an example of how we can introduce at, for instance, this stage, the subtraction property of equality, and at this stage, the multiplication property of equality, right? So take a minute to consider one of the other examples here and try it out for yourself. So let's also talk about classification of different types of equations. I mentioned that there's 3 different types, and so here they are. Our definitions are fairly simple. There is the conditional equation, which is an equation that's only true for typically one value. Now, there are other types of equations other than linear equations that say that you can have multiple different solutions. For this particular lecture, we're going to focus on linear equations, which typically are going to only have the one solution. So there's an equation that's true on the condition that x is a particular value. That's one type of equation. The other two are fairly similar, especially when we actually go to algebraically show that the equation is of one type or another. They are the identity and contradiction. So an identity is fairly simple to understand. If I end up with a statement such as x is equal to x, that means that any substituted value for x into that equation would make the statement true. Now this is an extremely simple example, but I think it illustrates my point. So if I let x equal 10, I get a statement that says 10 is equal to 10. If I let x equal any value, I get an identity. It is equal or equivalent to itself. So a more complex version of this type of problem you might see is something like 2x plus 1 is equal to 2x plus 1. Here again, if I let x equal 10, I get something like 21 is equal to 21. And it's clear that this is an identity if you stop to consider that I have the exact same expression on both sides of the equation. Now, it's not always clear from the outset that you have an identity equation, so some simplification may have to be necessary to prove that. And lastly, we have the contradiction, which is similar when we go to show algebraically whether or not a particular equation is of this type. In fact, what happens in both the identity and contradiction equations is that when I try to solve for my variable, it disappears. In my example I have written here for illustration purposes, I would, for instance, here try to move the variables to the same side here by subtraction. But what you'll notice is that I get 2x minus 2x. On the right-hand side, I just have now 1. And on the left-hand side, again, I get 2x minus 2x is 0 plus 1. So I just get this true statement, 1 is equal to 1. That is for the identity. And in fact, if I end up with a true statement and my variable disappearing, I can be sure that I've shown algebraically at least that I have an identity equation. For the contradiction, however, I might have the equation 3x plus 1 is equal to 3x minus 1. Now, in this case, any value that I substitute in for x will be multiplied by 3, but on the left-hand side, it's always going to be adding 1, and on the right, it'll always be subtracting 1. So no matter what value I choose for x in this scenario, no matter what real number I select, these two sides will actually never be equal. And so in the same vein as the last example, I can try to show this algebraically. If I want to solve this equation, I end up with 3x minus 3x is 0, so I get negative 1 on this side. 3x minus 3x is still 0, but I end up with a false statement, 1 is equal to negative 1. And so I've shown algebraically that there's no true solution to this equation. It is a contradiction. So here's a few examples for you to try. The very first example is the one I'll work for you here. So looking at the top example here, I see that I have lots of terms to distribute on either side of the equation before I simplify. Let's look at that distribution. So on the left-hand side here, I get something like 6 times 2x, and then 6 times negative 1. So 6 times 2x, that's going to give me 12x. 6 times negative 1 gives me negative 6, and plus 3. On the right-hand side, I'll just repeat that process here. I have 2x minus 8, and then my distribution. I get 5 times 2x is 10x, and then 5 times 1 is positive 5. So now let's reduce this a little bit further. On the left-hand side, my two constant terms add together. I end up with the statement 12x minus 3. On the right-hand side, I have some like terms. I have 2x and 10x that combine also to give me 12x. And then negative 8 plus 5. I actually get minus 3 in this case. So I'll sort of stop here and consider that this should actually be solvable now because I have the exact same expression on each side of the equation. 12x minus 3 is equal to 12x minus 3. So logically speaking, I've got enough information to determine what type of equation this is. This has got to be the identity equation because, yet again, if I were to try and solve this for the particular variable of interest, my variables disappear. Moving my variable 12x to the other side of the equation here requires subtraction. And in doing so, I end up with the true statement, negative 3 is equal to negative 3. So sure enough, I end up with a true statement, no variable. I've considered all the options here. This has got to be an identity equation. Take, for example, in contrast to this, the last example on the page. Actually, using the same logic, we can identify this equation as well. The initial statement I have here is something like negative 8x plus 3 is equal to negative 8x minus 9. Now, if I am just considering some arbitrary value of x, it looks like on both sides of the equation, I would multiply by negative 8. However, on the left, I'm going to add 3, and on the right, I'll always be subtracting 9. Since these two examples sort of contrast, again, I don't end up with a true statement if I were to try and solve this. By addition, I could say plus 8x on both sides, and I end up with the false statement 3 is equal to negative 9. Since this is not true, we know that this has to be the contradiction. So that is the contradiction equation example. And just to wrap up one more time here, we have the three different types and what happens when we actually go to solve for it. So the conditional equation will always end up with at least one value. So x is equal to some constant term. For an identity, our variable disappears and we end up with some true statement. What this suggests is that all real numbers for x would make the initial equation true. The contradiction, we actually also lose our variable in trying to solve for it. except we end up with a false statement, which says that basically no real number will be a solution to the equation.